Welcome to Real Physics. This is about the Machian Gravity Meeting recently held in Bonn with Dennis Braun, Jonathan Fay, Jan Preuss and myself. The talks and discussions are a little bit more technical than usual, thus if you're interested in the details I encourage you to look up my variable speed of light playlist or the papers linked in this video. Enjoy watching. Welcome to our meeting. I'm really glad to see here you all. And well, I want to just give a brief wholesale overview about the topic, definitely not going into the details, of which there are many, and why we are doing variable speed of light and why we are doing Mach's principle, why we are considering it. And there are definitely some big issues to be resolved, which conventional gravity theories cannot do. And I'm listing the big goals here. Some of them I believe we are already quite close to the solution, but the big picture does not fit perfectly yet, I would say. We certainly maybe this is conceptually the most important thing, the unification of inertia and gravity, and the origin of the gravitational constant is something that needs to be done if you want to have a satisfactory theory of physics of gravity. This is not just a God-given number, but it has to be related, and we have this intriguing coincidence with the data of the universe, so there needs to be a theory that predicts this constant. Also, the cosmological redshift is, I would say, even an anomaly that is to be explained, and certainly these ideas have the potential to give explanations. And let's not forget about the Dirac's large numbers. I don't think they are less significant than the coincidence relating the gravitational constant, but there are still many things to be done. It's not yet clear how such a theory of variable speed of light related to Mach's principle can reproduce all the effects of general relativity, and well, open end, so to speak. There is a plethora of unresolved cosmological riddles such as dark energy, also dark matter, of course, large-scale structure, many things that do not add up, and we might hope that a more fundamental theory of gravity could at least provide clues for resolution. And one important thing is, maybe it could turn out the most important thing, relating these ideas to a microscopic theory of matter, and I'm glad that Dennis will present some ideas about soliton solutions soon. Well, more into detail, or I try to remind of these important physicists, of these heroes that have advanced ideas about Mach's principle, and maybe the first to name is Dennis Sciama. Jonathan doing PhD work about his PhD, and I would say two of the major goals I listed earlier have almost be solved by Dennis Sciama. One of them explaining this coincidence of relating the gravitational constant, and the other one a long time overlooked by myself, and thanks to Jonathan and Jan I eventually realized that this indeed is a unification of inertia and gravity, as Jonathan has also worked out in his paper. Mach, of course, is the person to name here. I think you can also understand from his writings that he seeks this gravitational constant to be explained. Of course, I mean, he died in 1916. He hadn't even the possibility to realize that there is more than our galaxy in the universe. So he couldn't arrive, unfortunately, at a quantitative formulation of this, but I certainly believe that he would be glad about the ideas of Sciama. So this is not a small thing. I mean, let's put that into perspective. I mean, Newton realized once that this local acceleration is something bigger, and in the same manner, if we arrive at a sound theory that explains the gravitational constant as an effect of something bigger is not a small achievement. And I took away the factor 4 not to annoy Dennis here, but it could turn out in a different way. I mean, I'm not sure which one is the correct level. We have various versions here. And the conceptual unification is, of course, also, I mean, I would call it the explanation of the equivalence principle, because we have inertia here and gravity on the other side, and it turns out just two sides of the same medal, and that's certainly very satisfactory of Sciama's ideas. How we go ahead? Yeah, I mean, Einstein's considered or thought about the equivalence principle, and his first idea to fix that was variable speed of light. This is not his first, his second, but more important paper about the influence of gravity on the propagation of light. And how we can unify all this, I think this is one of the major problems. We should discuss how to get this together. Machian ideas along with Sciama, with the Einstein general relativity, and well, I guess we have to put the speed of light into the metric and extend it to a metric theory, as already Sciama tried, and Jan also a long time ago told about we need to insert the speed of light into the metric, and Jonathan also worked it out and published it. The key difference is here, of course, we are not reaching the Minkowski metric at the limit if you go away from the masses, because this would be, I think this is basically the wrong approach, and not the only aspect in which Minkowski messed up modern physics. I think he's one of the main culprits that something went wrong here. Anyway, I mean, that's certainly very intriguing, because we would have a divergent metric in the case, in the absence of masses. And well, I'm also glad that Dennis will talk about another idea related to Sciama, Hans-Jürgen Treder, who extensively worked on Mach's principles with an Lagrangian approach. This is the cover of his book. I mean, what we see here that he was not a marketing expert from the cover. But I'm curious to learn more about this approach. And yeah, let's not forget about Erwin Schrödinger. He was, I guess, the first one actually quantitatively relating the speed of light to the gravitational potential of the universe, speculating about that. And I guess he would be in agreement with the Treder factor. But we have also Robert Dicke here, and I don't think he is less important than the other ones. I think this is a really intriguing approach, and he independently from Einstein realized that variable speed of light can be combined with Mach's principle, and he explicitly speculated about the refraction index of space-time being 1/2 gm divided by rc squared, correcting Einstein's 1911 mistake. That's actually that's the factor 2 here. You need to reproduce the general relativistic effects. Einstein, of course, in 1911 couldn't be aware of this, but this was Dicke's first great achievement, I think, considering both lengths and time scales to be variable. And yeah, look at this. I think it's really beautiful to see the convergence of ideas, because Dicke is talking about index of refraction 1 plus and says, oh, this one is arising from the entire universe. And in Sciama, of course, these guys worked independently, and he said, he also talks about a refraction index of space is 1 over, it's the very same formula. And yeah, they didn't know about, and Dicke has the variable speed of light perspective, but Sciama nods, but I'm convinced that this is definitely just two viewpoints of one very important thing. And coming to Dicke's second great achievement, an explanation of the redshift. I mean, people nowadays, they don't worry about, say, okay, we have Hubble redshift and this, but this is something to wonder, something we should stop and ponder on. And it's an anomaly because nobody told the universe to expand in the first place. So that from a epistemological point of view requires explanation, and I think it's really a tremendous idea. What he says, basically matter is at rest, and the galactic redshift, the cosmological redshift, arising from that propagation of light, and light changes its properties with time. We have these variable scales, and yeah, I guess this is something to be included if we want to have a complete thing here. And yeah, this is just a visualization of the former Dicke idea. But here we're entering also the problems. I mean, I should say what I wanted to say in the beginning. There are two in physics or science, there are two different approaches. I guess once expressed by Heisenberg and Dirac in a discussion, and it's like climbing a mountain, and Dirac said, oh, if you climb a mountain, you have to do it step by step. If you don't reach the next level, you will never finish. And Heisenberg said, okay, but you also have to consider the wholesale picture. Look where you can go ahead and where not. And even if I appreciate Dirac more from the physics content, I guess Heisenberg has a point here, because we shouldn't lose the big picture. Anyway, if then we go to the details, and the next step, there are problems here arising, and it's a very interesting idea to say, oh, 1 plus a little something is the beginning of a Taylor series of the exponential. And this is the way that nicely explains also the perihelion shift of Mercury, as several authors have pointed out. Chris Kroch, a friend of mine in America a long time ago, Hall Puthoff, which I don't know personally, but has also developed a variable speed of light theory, essentially, even if he calls it polarizable vacuum. And another friend of mine, Markus Schönlehner, has also written an interesting paper about this, all with the same result. So there is this non-negligible fraction of physicists believing that there is something to that approach, a part of the exponential function. But on the other hand, unfortunately, if you take Dicke's approach directly, and this is the way that takes you to the explanation or a possible calculation of the gravitational constants, things don't add up, as Jan has worked out in detail and tried very thin a lot of things. I guess we all have tried very hard, but it seems it just doesn't come out, which is, yeah, something bad, because at the very end you want a perihelion shift to be explained. So this is a problem, definitely. And in this overview, you have the perihelion shift of Mercury unexplained by the sum approach. I still believe I wouldn't be eager to give up all the other explanations, because I think that that's so nice, that's so interesting, the perspective to calculate G and to explain the Hubble redshift, and also Dirac's large numbers, that, yeah, something has to be solved. We have to think about. And I also want to stress here that Dirac's large number hypothesis is something to be taken seriously. Dirac said such a coincidence, we may presume, is due to a deep connection in nature between cosmology and atomic theory. And not only that, it opens the way to these microscopic ideas. I have shown that Dirac's first hypothesis is actually equivalent, or maybe actually rewritten in a more intuitive manner related to the properties of the nucleus. Anyway, I mean, these two independent coincidences are, yeah, too much to make you believe in a pure coincidence. And by the way, they include the coincidence regarding the gravitational constant, but go also beyond, because you could realize the Machian coincidence with elementary particles that are 1 million times heavier, and at the same time 1 million times more in the universe. But this is something that needs to be explained. And but if you do so, I think there is, yeah, it can be very nicely explained if you just consider the variable scales you need. I mean, that's kind of logic. I mean, if nearby masses influence the speed of light, then of course we have this visually growing cosmos that also needs to lower your speed of light. So necessarily you have a change in frequencies and necessarily have a speed and have a change in wavelengths. So, and this, yeah, leads you, I don't go into the details, you probably know that you have the perceived time, and that t to the, with this exponent 0.75 leads you to the seemingly number of particles seemingly proportional to the square of the perceived time, because I don't have the cursor here, but you see where is the volume here, or the cosmic horizon goes to t to the exponent 0.5, and you have a volume, so it would be 1.5, and this is just squared the 0.75. So at the very end we have, I mean, this possibility to account for Dirac's large numbers. But on the other hand, I don't want to hide the problems, and there is another huge problem I recently came across, because if you just do it cleanly, calculate the respective redshifts, and in this table you see redshift starting with 0.01, so we have your lambda is actually 1.01 larger than lambda 0 back then it was emitted, but due to this square in the equations you have the radius back then when the light was emitted was at 0.98 of today's radius, and so on. And then you look at the time at your clock, and it turns out that the light with the redshift 0.01 was emitted at a time 0.97. So, and then you calculate the distance to the distance back then, and unfortunately it really doesn't match. So what I was hoping for to get a better fit to galaxy data, but it's just way off. So this is the kind of a square root that messes up everything, which basically seems to be linear. But I mean, well, this is to be fixed, definitely. And there could be, of course, a major misunderstanding or misinterpretation or something even more fundamental. I don't know. Just, I mean, with all the euphoria of the potential, we have to be aware of the problems at the same time. So yeah, to sum up, which version is correct? I already mentioned the exponential versus the sum approach and the perihelion advance of Mercury. We need to have a consistency with general relativity, and this is something we maybe need to discuss. Which is the correct factor? Is it 1/4? Is it 1/3? And yeah, and so on. How do we extend it to a relativistic theory? Does a vector potential, is it sufficient, or do we need a metric? I mean, I guess we need a metric, but it has to be worked out. We, of course, need to be in agreement with the data, and yeah, compatibility with electrodynamics is another interesting topic, but it's maybe a sideline, because once you go into variable speed of light, you have also varying constants of electrodynamics. And maybe the most important unsolved problem, I mean, at the very end, we need a microscopic theory of matter, a model that also explains somehow, I mean, what is an elementary particle? How is this quantity of mass, how comes it to birth, and how such a defect or solution or whatever it is, how does it create the gradient in the speed of light that is responsible for acceleration? I mean, there are a whole lot of other problems to solve, but I think, yeah, these are maybe the important ones. I should mention that I fear that we cannot stay at this point with Euclidean space and Euclidean time. There might be a fundamental misunderstanding also here, which messes up the things. But yeah, let's try at this point follow Dirac and get to the next level, at least to a reasonable thing. And yeah, one last thought is that it might be that we live in a time where we have not very much time left to explain it with the human mind. I don't know. It's certainly exciting from one point of view, but also a little bit scary. And on the other hand, we are in a fantastic period in which we can tie all the bits together. And these guys, unfortunately, they had no internet, and Schrödinger was unaware of Einstein, and Dirac was unaware. Nobody communicated. They didn't talk about their best ideas, and this is really a pity. And we see these coincidences, we see these similarities, and I think it's really an exciting task to think about how to get all this together. And I'm very glad that you're collaborating here. Thank you very much for this meeting. Okay, yeah. Any questions or comments?
Yeah, I have a few, but go ahead. Well, a few different comments. So, some questions, some kind of comments. So there's this.
Should we? You want to?
It's okay. I mean, yeah. I'm in the next one.
Okay. Yeah.
So there's this question with Dirac's large number hypothesis. So I think that historically this was a motivation for Jordan.
For mine?
Jordan.
For Jordan. Yeah. Jordan was actually working on this hypothesis. I even have a quote. Jordan said that this is one of the most significant results of modern physics, and we all should stop and think about. And yeah, but there's this interesting historical connection, because then Jordan develops this scalar tensor model of gravity that then is reinvented and sort of fused with Dicke's Braun and Dicke's model of gravity. It essentially becomes the same thing. I think the way they do it is they just have GR with a variable gravitational constant. Okay, I wasn't aware of that. Interesting. Yeah, I just know that, I mean, Jordan published his volume Schwerkraft und Weltall, which is Gravity and the Universe, and he was very interested in, and well, actually, there is a misunderstanding to avoid here. I mean, everybody unfortunately talks about Braun's Dicke and the Braun's Dicke theory, and it got worldwide reputation because Dicke was also a spectacular, very good observational physicist. But I guess my personal impression is that it was unfortunate, let's say, that Braun's collaborated with him, because he took him away from a really interesting idea, which is his 1957 paper. And the other theory is just something that didn't work out. And it's also, I mean, I see no real fascination here from a theoretical point of view. They really clean realization of Mach's principles, I guess, in the earlier paper. Yeah.
And in Sciama's work. And I think that's also a feature of Dicke's writing. He has all of these interesting ideas, but he sort of, if you read his papers, he fuses like loads of different interesting things, but then doesn't really get down to the foundation of why is Max, like he doesn't really ask the deeper question, like why is this even justified, why is this really interesting, and dig into it. He just kind of has a lot of different heuristics to work with. So it's not like such a fundamental theory, but they do sort of create this model which is potentially more accurate, so it has some kind of predictions. But it's interesting historically that the Mach's principal motivation and the Dirac large number hypothesis sort of converged insofar as like the Jordan's theory and Braun's.
Yeah, I mean, Dicke mentioned Dirac's large numbers, but unfortunately, I mean, he just miscalculated here, and instead of confirming Dirac's large numbers, which he could have done easily if he realized that's the perceived time. Yeah, I have a paper out there which is Dicke's consequential error, and instead of confirming that fantastic result of Dirac, he got in a pity debate, in a pity argument with Dirac, and saying no, you're not right, and just a little flaw. And Dirac even took the time to go into the paper. He would have discovered the flaw, but he just opposed, and this was
Dirac, interestingly, was Dennis Sciama's supervisor.
Yeah.
They didn't talk that much. I get
Yeah. Well, Dirac didn't talk at all.
Exactly. So apparently, Dirac managed to somehow inspire Robert Dicke.
Yeah.
In the few times he did.
Yeah. The famous quote by Bohr. So we had wonderful discussions with Dirac, in which practically all the talking was done by Bohr. No, Dirac said I had wonderful discussions with Bohr, and all the talking was done by Bohr.
And then.
But you believe in the significance, as I understand, of Dirac's numbers. That's something.
No, I think. And I do think that these variable G expressions that come out of these Machian theories will are very likely to explain that.
Yeah, because unfortunately it's really dismissed too often. That's also, I mean, kind of a cultural problem. I remember an anecdote. Professor Hans-Dieter C., who was in Heidelberg before, he was also very interested in Mach's principles. I guess it was back in the 70s, and he had also read Jordan's work, Schwerkraft und Weltall, and then there was the spacecraft discovering the surface of the moon, and he was and there were interesting results about could there be Earth expansion theories and this and that, and he was enthusiastic and talked to Feynman and said, isn't that interesting, and couldn't that be related? And he was just dismissive, like who is that? And no, we know better, and very, very arrogant, but you need to take these messages of natures. You need to take them seriously if you want to. make progress.
And so what I've always thought might make more sense is if really the expression is 1 plus mg over rc squared, all squared, right? And then the first two terms.
Yes.
Of course. Yeah. Mm-hmm.
Is that what you have as well?
Right.
Yeah.
Yes.
Yeah. I mean, that's precisely the point where where the ways dividing. You know. I mean that if you speculate about this to be the beginning of the Taylor series, you lose that other possibility, which is I am in agreement that this is the more interesting thing. That's the result of a square here. But yeah, I mean, just the two here you just need it for being in agreement with the tests of general relativity.
Yes.
Yeah. But where it really comes from, that is precisely the question. Yeah.
And that's what I ended up having, like in my metrical
Mm-hmm.
model. That
Mm-hmm.
That because you have this
Mm-hmm.
whole expression squared,
Mm-hmm. Mm-hmm.
it just becomes the total gravitational potential including the nearby mass,
Mm-hmm.
all squared.
Mm-hmm.
And then all of your terms in your metric
Mm-hmm.
are just squared terms.
Yeah.
The
Yeah, but we come back to that
because
in-
the metric
Yeah.
is dx squared. Right?
Mm-hmm. Yeah. Mm-hmm. Yeah, we come back to that in detail. Surely, also with off camera, so we are more free. But Dennis, you have a comment? Still?
Yes, it was basically just for this factor which appears in the formula for the gravitational constant.
Mm-hmm.
I don't think that this is too much of importance if it is a factor of 2 or 4 or 1. It will eventually just come out when one has the complete theory. But I think one does not have to, argue or discuss now too much if it is a factor
Mm-hmm.
of 2 or a factor of 4
Mm-hmm.
or 1. It will just eventually come out
Mm-hmm.
from the correct theory, whichever it will be then.
Mm-hmm.
And also I think that one should not worry about an exact agreement with the experiments too much at a too early stage. Of course, one has to keep this in mind, that the correct theory has to correctly describe all the experiments. But if one focuses too early on agreement with all the experiments, then maybe one loses some interesting ideas, which on first sight disagree with the experiments, but
Mm-hmm.
on second sight they do. One famous example would be the continental drift of Wegener,
Mm-hmm.
which was dismissed because the people said, yes, the Earth must be solid because it transmits seismic waves. But it turned out that it only needs to be solid on
Mm-hmm.
a small time scale, and it was not really a counter-argument
Mm-hmm.
to the correct theory.
Mm-hmm. I see. No, I'm perfectly in agreement with you, and I mean, I'm the one challenging the so-called evidence for, I don't know, neutrino oscillations, whatever, dark energy. It's kind of a difficult task to draw the line. Where's the solid evidence, and you can't spend your life repeating everything which is obvious, and where is the solid part of physics, of observational physics, where is this speculative or sociological knowledge which has been established?
Yes.
And I'm talking about, baryonic acoustic oscillations, or shouldn't name it here, but gravitational waves. I still have some reservations, and I'm fine that we shouldn't care about at this stage. How do you reproduce that gravitational waves or this and that? On the other hand, I mean, there is not only some evidence to this general relativistic effects, and this need to be accounted for. And of course, it's not a matter of debate of arguing, but of calculation at the very end, and it should be determined. It should not just be fixed because it comes out in the right way. So we want something with explanatory power here. Yeah, agree. You have some comments?
Let me just quickly return to this 1 plus mg over rc squared. So the problem really is the perihelion shift of Mercury here. Unfortunately, with the exponential function, you easily arrive at the correct perihelion shift that is also predicted by general relativity, and it just doesn't work out with this formula because it's the only second order effect of general relativity we can directly observe. And of course, in the second order of this expression, the exponential function will be different from this simple sum.
Yeah, I mean, I agree so far that this is the problem, and I mean, of course, we could, following Dennis' spirit, say, okay, let's not be too close, but this is 1859, and you kind of lean out of the windows if you put in doubt wouldn't put in doubt the perihelion, which has been measured in multiple other occasions. So, but on the other hand, I mean, we also need the freedom to just think about and leave it aside, but it has to be flagged and a red flag as a serious problem. Yeah.
Right. I don't like the exponential that much myself, but we just have to acknowledge this problem. And this relates to something else I wanted to comment on. So you said we would have to have compatibility with general relativity, but general relativity has actually only been well tested for the weak field. So we would have to reproduce all classical tests, but there could be larger differences for the strong field.
Yeah, I guess I agree. However, there are also claims regarding tests of strong gravitational fields with pulsars. There is even a professor here in Bonn, Michael Kramer, dealing with the pulsar physics, and I guess he has some additional claims related to it. But okay, I mean, we should be aware of, but take everything with a grain of salt, which is not settled for 50 years at this point, because I mean, if you really dig into the fundamentals, I mean,
sure, there are also claimed observations of black holes and these kinds of things, but maybe we can agree that the weak field is well tested and probably beyond doubt, and this is not the case with the strong field.
Yeah. Regarding black holes, I mean, we should mention here Wolfgang Kundt, who is also in Bonn. He has a very sound critique of, well, the observational evidence for black holes not being very different from the neutron stars, and I think he has a point here. Yeah. So we have evidence such as the Sagittarius black hole in the center of the galaxies. We need to be aware of the evidence, but on the other hand, you don't make progress, I guess, if you stick too close at all recent claims. Yeah.
But I take it that the Schwarzschild metric predicts the right perihelion shift.
Yes, that's sort of by accident. In the second order term, the Schwarzschild metric produces the same term as this exponential function.
Right.
It's different, but it has the same second order coefficient.
But so, I mean, what I've been basing my stuff is on making sure that I recover the Schwarzschild metric in the right conditions, or something close enough to it.
All right.
That it's not substantially better.
Yeah. If you manage to reproduce this up to the second order, then it will work out fine.